Hello and welcome to By Excellence Tutorials with your one and only, the By Excellence tutor. Well, in this video today, we're going to look at rotational dynamics. So rotational dynamics, basically you're looking at motion in a circle or in a circular path. Not only do you look at motion, but you also look at what is causing that motion. And in a circular path, just like in linear motion, we talked about dynamics or the force, Newton's laws or Newton's forces, where we had forces causing motion. For an object to move, we needed an external force to be applied on the system that it moves. Otherwise, it was going to be at rest and continue being at rest. Now, what about an object that is moving in a circle or in a circular path? It needs also something equivalent to force in linear motion that will cause it to move from one point to another in a circular path, and that is a torque. Well, have you yet subscribed to the YouTube channel? If you have not yet subscribed to this YouTube channel, kindly do so. And don't forget to click on the notification bell so that you get notified once I upload new content. Well, let's get into the business of this video. So we have a question, says a force of 2.2 Newton acts tangentially to the rim of a solid 52 kg disc that has a radius of 32 centimeter. And the first question says, how long does it take to accelerate the disc rotating about its usual axis from rest to 210 rev per minute? All right, so what is the first thing that we have to do? The first thing we have to do is to illustrate, is to visualize, to have a mental picture of what this question is asking us to find. Well, so let's try to visualize this. So we have so assume that this is really round, it's a circle. So this is a disc, and let's say we have a force 2.2 Newton, and this disc has got radius of 32 centimeters. All right, this disc as well is 52 kg. Okay, so now for this disc to rotate, it needs this force. And now what we're looking for is the time. How long does it take? So it's the time. Now, how do we get the time? So we need, looking at the data that we have force 2.2 Newton, and we have mass 52 kilogram. We also have the radius 32 centimeter, which can be 0.32 meters. And we have also the initial angular velocity. We've been told that this disc has started from rest, it's coming from rest. So if something is coming from rest, it means the initial angular velocity here is 0 rad per second or rev per minute. All right, so let's put it into rev. So 0 rev per second, and the final angular velocity is 210 rev per minute. Now, we need to also convert this per minute into per second, so that it should be rev per second. All right, so that we get maybe time in seconds and so on. All right, so how do we convert? We know that we're going to have rev per minute. We know that in a minute we have 60 seconds. So here we're just interested in converting minutes to seconds. So it will end here as in the conversion factor is concerned. So Once you do that, what you get is actually 3.5 rev per second. Okay. So now, another thing is for us to also note about the moment of inertia of the system, of this disk. So we know that the disk, the solid disk, has got the moment of inertia of half by the product of its mass and square radius. So that's the moment of inertia equation. All right. So now, having all this data, we can be able to get started now. So how do we get started? We start with torque now. We know that torque is given by force times perpendicular distance. Not only is torque given in form of force and perpendicular distance, if we take back to, I take you back to looking at work done in a circular motion, you are going to see that torque as well is given as moment of inertia times the angular acceleration. So in this case, for us to get to time, we find first the angular acceleration. From angular acceleration, we can get the time, the how long the question is asking us to find. So when you look at these two equations, equation 1 and equation 2, you're going to notice that these equations are the same or are equal. All of them, they are for torque. So we equate the right-hand sides of this equation, and we're going to have inertia alpha being equal to force times perpendicular distance. So now we divide by inertia both sides, and we are going to have angular acceleration being equal to force times inertia. Now, the force is 2.2 Newton, multiplying by the radius, which is 0.32 meters, over the inertia, which is half the mass of the disk, 52 kg, and the radius, 0.3 meter squared. So what will be our angular acceleration? So our angular acceleration, if you punch here, you are going to get 0.2644 rad per, so we have the Newton there, so it's going to be rad per square second. All right, so maybe you are confused there, but how has it come up with the SI units and all that? So we know that a Newton is it's actually the mass, a unit mass, which is kg, moving with a velocity of 1 meter per second. Sorry, not the velocity, but the acceleration of 1 meter per square second. And we have also the meter there, and we have the kg down and the meter squared. So meter by meter here, it will give you squared, which will cancel with this, and kg will cancel, and you have per square second. So per square second, then you have a rad. All right, so I just wanted to make sure that you are not lost to say, how has he just decided? It's not basically just deciding on what SI units to use at the end. All right, so we have rad per square second, but when you look at your data, you have everything to do with revolutions. So now, what we do is to convert this into rev. So the conversion factor as well, what we know? We know that one revolution is 360 degrees, which is equal to 2 pi rad. So we know that 1 revolution is equal to 2 pi rad. So you punch that one, and what you're going to get, you're going to get 0.042 rev per square second. So this is our angular acceleration. So from the angular acceleration, we can now be able to get what's this? The time that we are looking for. All right. So how do we get the time that we are looking for? Now, we know that angular acceleration, or let me use, even this one, angular acceleration is given by the final angular velocity minus initial angular velocity over change in time. So we make t the subject, and we're going to have angular times c equal to that minus that. We divide by angular acceleration throughout, and we are going to have time being equal to like that. All right. I think I was supposed to write this equation first so that you know that we were missing angular acceleration. So I just did it as if you know already. Sorry about that. But I was supposed to write, I think, this formula so that you know that what we were missing is the angular acceleration. Because I know someone will be like, but why doing or finding first angular acceleration? That is what we were missing in our question. All right, so I'll come here, and the time is going to be final angular velocity. What is it? Okay, so we have 210, no. Oh, we have already converted. So we have 3.5 rev per second minus, it is coming from rest, so it's rev per second, 0 rev per second over 0.042 rev per square second. So our time is basically going to be 83.2 seconds. All right, so this is how long this is going to take. Okay, and then now we are being asked about the number of rotations. All right, so how do we get that one? That one is pretty simple at this stage because we have everything we need to calculate that one. All right, so you can use any of the formulas to do with the revolutions. So we're going to have, so the revolutions, basically the angular displacement. All right, I thought of mentioning that. So we have this formula. All right, this is not the first time you're seeing this. You know, this one, it's coming from linear and all that. All right, so the initial here is 0 rev per second, and we have the time 83.2 seconds plus half, and angular acceleration 0.042 rev per square second times the time. And what is our time? Our time is 83.2 seconds squared. So the first term here we're going to get is 0 because we are multiplying by 0 there. So everything you multiply by 0 becomes 0. So the far end here, it's giving us 145.367, blah, blah, blah. So this is going to be 145.4 rev. Okay, so that is how you get to find that question. I believe it was not hard to solve that question. And if you've liked this video, kindly give it a reaction, give us the feedback, share with your colleagues so that they can be able to enjoy and benefit as well from our videos. All right, so we'll see you in the next video. Thank you for your time.